You're made of atoms. Everything you see, touch, breathe, or think, it's all made of atoms. And if you zoom in far enough, something strange happens. Because the closer you look, the less sense the universe makes. Welcome to the quantum world. Here, particles pop in and out of existence. Light behaves like a particle and a wave. Objects can be in two places at once. And sometimes, two particles on opposite sides of the galaxy somehow know what the other is doing. It sounds like magic, but it's not. It's quantum physics, the most accurate, mind-bending theory ever built. The word quantum comes from the Latin quantus, meaning how much. In physics, a quantum means the smallest possible piece of something, a single packet of energy, like a pixel of reality. The world seems smooth and continuous to us. But at the smallest scales, nature is grainy, made of tiny, indivisible chunks. At the start of the 1900s, scientists tried to explain why heated metal glows. Classical physics said the brightness should shoot to infinity. It didn't. So Max Planck made a daring guess. Energy can only be released in discrete packets, quanta. It worked. Energy itself comes in steps, not a smooth flow. That one idea, meant as a quick fix, cracked open a new universe. Then Einstein jumped in. He realized that light, which everyone thought was a wave, could also act like a stream of particles, photons. Shining light on metal kicked out electrons, but only if the photons had enough energy. No matter how bright the light, if the photons were too soft, nothing happened. This was proof. Light behaves like both a wave and a particle. The universe had just broken its own rules. A few years later, Louis de Broglie turned the idea inside out. If light can act like particles, maybe particles can act like waves. Turns out, they can. Even solid matter has a wave nature. And that discovery led to one of the strangest experiments in all of science. Imagine firing electrons at a wall with two slits. If they're just little balls, you'd see two stripes. But instead, you get an interference pattern like ripples on water. The electrons act like waves passing through both slits at once. But when you when you measure which slit they go through, the pattern disappears. They behave like normal particles again. Simply observing changes the outcome. This is the observer effect. The act of measuring forces nature to decide. Before observation, each electron exists in all possible states, a superposition of possibilities. When we look, it chooses one. In other words, the universe doesn't commit to a reality until it's observed. That's not philosophy, that's quantum mechanics. To show how ridiculous this sounds, physicist Erwin Schrödinger imagined a cat in a box. Inside is a radioactive atom that may or may not decay. If it decays, a vial breaks, poison is released, and, well, goodbye cat. If it doesn't, the cat's fine. Until you open the box, the atom is both decayed and not decayed. So the cat is both alive and dead. It's not really about cats, it's about how observation affects outcomes. The world only decides when you look. Now let's crank the weirdness up another level. Entanglement. When two particles interact, they can become linked. Their properties forever connected. Measure one, and you instantly know the other, no matter how far apart they are. It's as if the universe keeps a secret thread between them. Einstein called it spooky action at a distance. He hated it, thought it couldn't be real, but it is. We've tested it thousands of times, and nature keeps proving Einstein wrong. Entangled particles don't send messages faster than light. They're just two halves of the same quantum system, sharing a single state. Space doesn't seem to matter to them. So what is actually happening down there? Quantum mechanics doesn't tell you where a particle is, only the probability of finding it somewhere. That's described by the wave function, written as psi. It's like a cloud of possibilities spreading through space. When you measure it, the cloud collapses and one outcome becomes real. This isn't ignorance, it's built into nature. The universe itself plays by probabilities. That randomness might sound like chaos, but it's not. Quantum theory predicts outcomes with absurd accuracy, more precise than any other theory in history. Every laser, transistor, and smartphone chip depends on it working perfectly. In other words, the weirdness runs the world, but the rabbit hole goes deeper. In modern physics, particles aren't tiny dots. They're ripples, excitations in invisible fields that fill all of space. There's an electron field, a photon field, a quark field, and we are just waves rising and falling within them. A particle is simply a temporary vibration of that field, like a ripple on a pond that appears, moves, and fades. This is quantum field theory, and it's our best description of reality so far. But even waves have limits. The Heisenberg uncertainty principle says you can't know both a particle's exact position and momentum at once. The more precisely you know one, the fuzzier the other becomes. It's not bad equipment, it's the universe's own rulebook. At the smallest scales, things don't have definite properties until measured. And ironically, this uncertainty is why atoms even exist. It stops electrons from spiraling into the nucleus. Without uncertainty, everything would collapse. All of these ideas combine into the Standard Model, a chart describing every known fundamental particle and how they interact through forces: photons for electromagnetism, gluons for the strong force, W and Z bosons for the weak force. But one big piece is missing: gravity. Quantum mechanics and Einstein's relativity don't get along. Reconciling them into one theory, a quantum gravity, remains one of science's greatest quests. Meanwhile, we've learned to use the strangeness. Quantum tunneling lets particles slip through barriers that should be impossible, powering flash drives and nuclear fusion. Quantum computers use superposition and entanglement to process information in ways classical computers never could. Quantum teleportation has been demonstrated between particles, transferring quantum states instantly. No, we're not beaming humans across galaxies, but the principle already drives next-generation communication and encryption. It's wild to think. The same physics that governs electrons and atoms also built the entire digital age. Quantum physics isn't just weird theory, it's the foundation of modern life. And yet, even after a century, we still don't truly understand what it means. Does observation create reality? Is randomness fundamental? Are there infinite universes where every quantum possibility plays out? Maybe. Or maybe our human brains just aren't wired to grasp what's really going on. Quantum physics shows us something profound, that the universe doesn't behave the way we expect. It doesn't follow our intuition. It writes its own rules. Reality isn't made of certainty, it's made of probabilities, of connections, of endless potential. So the next time you flip a light switch, send a text, or just stare at the stars, remember that deep beneath all of it, the universe is buzzing with invisible waves, particles, and possibilities. The rules of the impossible are the rules of everything.